Okay, so in this question, we are going to be discussing the following topics. Specifically, we are going to be evaluating zeros of a function, the zeros of a function, and their multiplicities. So if you have not, if some of this seems a little bit foreign to you, go ahead and research or evaluate in your textbook and determine where the multiplicity section is of a zero, and that'll help you in this question. So notice here the question states, find the zeros of the following function, f of x, and then state the multiplicity of each solution. And notice this term solution is also another term that is synonymous with a zero. So if you would have seen zero, solution, or x-intercept, those all would have been synonymous. So in order for us to find where this function equals zero, or it has a zero or crosses the x-axis, we're going to have to set this guy equal to zero. So we're going to have to set him equal to zero, and that way we can actually determine, where this guy equals to zero. Sorry about that. So where this guy equals to zero. So according to our zero value theorem, we have one term, two terms, three terms, and four terms. And we can set each one of these equal to zero since we are multiplying each one of them independently equal to zero. But we have to be careful. We have to be careful because notice here I have the same zero multiplied out twice. So hopefully some of us recognized that we have the same term being multiplied out twice. But for right now, that's okay. We still can find the zeros. So notice here, if we want to solve, we're going to divide both sides by 2. So we get x squared equals to 0. Take the square root of both sides. So x would equal to plus or minus 0, but we can't have plus or minus 0, so it's just 0. So in order for us to solve this guy, we're going to raise both sides to 1/3 power. Raise both sides to 1/3 power, so we get x minus 3 is equal to 0, or x equals to 3. Here's our second zero. That's our first zero. Notice we're going to do the same thing over here, but we're going to raise both sides to the 1/4 power. So we get x minus 3 equal to 0, or x equals to positive 3 again. So notice that 3 is repeating. Then lastly, we're just going to add 1 on both sides, and we get 2x is equal to positive 1. Divide both sides by 2, and we get x equals to 1/2. So notice here we have x equals 0, x equals 3, x equals 3, and x equals to 1/2. When you went over this section, you should have recognized something at the very beginning, and that was in this section we have x minus 3 and x minus 3. So I'll just underline them. X minus 3 times x minus 3. So in reality, what I really have here is I have f of x equals to 2x squared times x minus 3 cubed times x minus 3 to the 4th times 2x minus 1. And what you can really do in this circumstance, let me erase that so it looks better. What you can do in this circumstance is you can actually combine these two terms together because they have the same base. The same base is a binomial raised to an exponent of 3, and this one's raised to an exponent of 4. So we can combine them and say we really have 2x squared times x minus 3 to the 7th times 2x minus 1. And notice this would have combined these two zeros. So if you would have seen this very beginning, excellent, awesome job. This will help determine the multiplicity. So what I like to do next is I like to set up a table. So I'm going to set up a table. I'm going to give my 0 over here, and I arrange them in ascending order. So notice my first zero occurs at 0. My next one is at 1/2, and my last one is at 3. And I'm going to do my multiplicity in blue. So for 0, my multiplicity is how many times this occurs, and I look at the exponent because that exponent is going to indicate to me how many times that 0 occurs. So in this first guy, my 0 has a multiplicity, my 0 of 0. Oh no, what did I just do? Oh, I have a frozen screen here. Hopefully it recovers. Okay, it recovered, thank goodness. So here we're going to have a 0 of 2. For 1/2, that's going to correspond to this 0 over here. And notice that exponent's a value of 1. And then for 3, we have to be careful. Notice here, this 0 occurred 3 times. Then over here, this 0 occurred 4 times. 3 plus 4 gives us a value of 7. And notice here, that's also consistent when we put it together. So this one's a little bit trickier in the fact that we have to actually determine what that 0 of that of that 3 is. The 0 of 3. We have to determine what that multiplicity is. So I often like to state whether or not these are even or odd. And this guy's even, this guy's odd, and this guy is also odd. And this can actually help you determine, we'll do the action of the graph in green. So the action here will be, if the multiplicity is even though this question not asked for this, we can go ahead and do it just to make sure we know it. The action here will, at the 0, the graph will just touch. If the 0 is even, if the multiplicity is even, that 0 will touch the graph will touch the axis and bounce off. It's tangential. If that 0 has a multiplicity that's odd, the action of the graph will actually cross the x-axis. And then here at 3, the multiplicity is odd, and therefore he will cross as well. So even if we just do a quick depiction over here with our 0 at 0, I'll do my zeros in gray. So I have a 0 here. That's not very good. I'll use black. So I have a 0 here. Then I have a 0 at 1/2, and then I have a 0 at 3. I know based off of my leading term test, I can use my leading term test. I recognize here I have an x squared. Here I have an x cubed, here I have an x to the 4th, and here I have an x. If I multiply each one of these together, I'm going to add the exponents. 2 plus 3 is 5, plus 4 is 9, plus 1 is a value of x to the 10th. We know that function has to start up here in quadrant 2 and leave in quadrant 1. So if you haven't done the leading term test or you're not familiar with it, go research your leading term test. And notice we also found that consistent here. This has an exponent of 2. 2 plus 7 gives you 9. Plus 1 gives you 10, so you're going to have that same x to the 10th. So we know he's going to start up here in quadrant 2. He's going to come down. At 0, he's just going to touch and bounce off. At 1/2, he's going to come down here and cross. And then at 3, he's going to come back up and cross. So he's going to end up coming back out. So notice here at 0, he just touches. He just touches here at 0. At 1/2, he actually crosses because he says he's going to cross based off the multiplicity being odd. And then at 3, he is also going to cross. So now let us go on to the next question. So next question is number 12. And number 12 asks us to determine if the following function is 1-to-1. If it is, determine the inverse function. So if you were to research some topics in this section, you could research inverse functions and 1-to-1 functions. So a 1-to-1 function is unique because the function f of x has an inverse, f inverse of x, which is also a function. And the way we prove this is that we know f of a must equal to f of b for all a equaling to b. So this is the way that we prove a function is an inverse, a function is 1-to-1. So here, let us find, we'll do this in red, we're going to find f of a. F of a is equal to, everywhere we see an x, we plug in a, we're going to get a cubed minus 1. And notice here, that should be minus 1. And then f of b will equal to b cubed minus 1. So what we have to do is we have to set f of a equal to f of b. So we know a cubed minus 1 will have to equal to b cubed minus 1. We add 1 on both sides, so that goes away, that goes away. So we get a cubed is equal to b cubed. And we can raise both sides to the 1/3 power. And these will cancel. And we get a is equal to b. And that is the check that we were looking for. Therefore, f of x is 1-to-1. So since f of x is 1-to-1, now we want to find the inverse function. So let's go ahead and find the inverse function. So we have to find f inverse of x. That's what we're going to be looking for. So rules. So our first rule is replace. We're going to replace f of x with y. So this question did start off with f of x equals x cubed minus 1. So we're going to say we have, y, which equals to, oh, look at that. Make that better. So this will be x cubed minus 1. Our next step is we're going to change x with y, and then for every y, we're going to replace that with an x. So in that circumstance, we're going to say x is equal to y cubed minus 1. In step 3, and this is rules for finding our inverse functions. Step 3, we're going to solve for y. Solving for y, we're going to have to add 1 on both sides. So we get x plus 1 is equal to y cubed. And then in order for us to solve this, we're going to have to take the third root of both sides, which is the same as raising to the 1/3 power. Raising to the 1/3 power is the same as taking the third root. So if you don't like the 1/3 power, I will go ahead and I will take the third root of both sides. Oh, a little bit of a technical difficulty there. There we go. So I'm going to take the third root of both sides. The third root of y cubed will cancel, and then we will have y is equal to the third root of x plus 1. And then lastly, we will replace y with f inverse of x. So here I can say that y, which will be equal to f inverse of x, is equal to the third root of x plus 1.